welcome once again. Let us continue our discussion as lecture 14, bonding and electronic nature in bent metallocene. In the last class, you remember we discussed the what are the parameters for the bent metallocene and what are the structural variations in bent metallocene. So, now we will try to understand that what are the difference in orbitals and the electronic nature between the parallel and the bent metallocenes. Okay, as I told that understanding of orbitals in bent metallocenes is very important to understand the mechanism and the reactivities associated with bent metallocene, because the catalysts are actually the bent metallocene. So, this is very important to understand. Okay, so, let us try to understand this. So, this is, you see that this is the D5H, that is the Eclist form, okay, as example ferrocene, where two CP ligands are parallel, and this is the your bent metallocene. So, this is the parallel and this is the bent metallocene, and you see that the point group is C2V. C2V is the actually highest possible symmetry for a bent metallocene. So, we will discuss, okay, we will try to understand the MOs with the most symmetric bent metallocene system. Okay. In the last class, we discussed that how it is C2V. So, you will see this is your C2, okay, and then this is your the sigma V plane, this is sigma V, and this is your C2 axis. So, it is easy to understand why it is C2V. Okay. So, there are a lot of examples of this kind of bent metallocene, as example like zirconium, tantalum. Okay. So, this is your 4 oxidation state, this is 5 oxidation state. Particularly, we are very interested to understand the MOs and electronic nature for the zirconium, that is the group 4 metallocene, because most of the metallocene catalysts for olefin polymerations are actually based on this. Okay. But we have to design, okay, our catalyst to get the desired polymer with desired tacticity, that we will understand. Okay. So, let us discuss. Now, in the last class I mentioned that some of the structural parameters which actually is used, which are helpful to quantify how much bend the metallocene is, as example this alpha angle, this beta angle, or also this angle. Okay. So, these are very important when, and these parameters will be useful to design a new catalyst. Suppose I need a lower beta angle or higher beta angle. So, accordingly I will choose my the bridging atoms or number of bridging atoms. Okay. So, these are very important, because as I told that depending on the beta angle, it will the openingness of here, this case openingness of the metallocene will also be changed. Fine. So, let us try to understand what will happen for the molecular orbitals. If you remember that for molecular orbitals of the parallel ferrocene, so these three set of orbitals are very important. Okay. So, this E2 involve the dxy and dx square minus y square orbitals. Okay. So, if we see the axis, okay, here, okay, this is, I think this is fine. So, this is I think I should mention the axis. So, z x y, okay, the Cartesian coordinate. So, here you see that depending on the number of electrons filling up the electrons in E2, A1 and E1 star for parallel metallocene, actually the structural and reactivity will also vary. As example, like for ferrocene, we saw in the last classes that all the bonding orbitals, okay, are filled it up. So, for ferrocene up to this one is filled it up. Okay. So, all the bonding orbitals fill up, and that is why very stable. If we can put electron here, okay, then we are putting electron to a antibonding orbitals, then obviously the system will be destabilized. However, as I told many times that here, although we are telling the antibonding E1, but the antibonding nature is comparatively less, okay, for E1, okay, star for the metallocene, and similarly for A1 E2 the bonding character is relatively less, and we discussed that one. Fine. Now, what will happen if the symmetry changes from the D5H parallel metallocene to the C2V bent metallocene? Okay. I will try to discuss in a very qualitative way. I am not going to use the group theory here, very qualitatively, so that everybody can understand. Okay. So, and also I am considering the most symmetric bent metallocene, that is the C2V. Okay. Now, what will happen here? What will happen that these are the filled d orbitals, okay, generally. So, out of these three, 2 filled orbitals, okay, will mix it up due to the bend, mix it up, and it will be apart in energy. So, they will mix and so this is, so 2 orbitals out of these 3 d orbitals. So, 2 filled d orbitals will mix due to bending of metallocene, okay, and it will be one component, that is the A1 will be in higher in energy, this one, and one component will be lower in energy. Okay. That means, you will see that from here. So, one component the symmetry was E2 and another A1. So, from here one will be the 4A1 and another will be the 3A1. So, one will be higher in energy, and one will be in lower in energy. Okay. And the third orbital, okay, that is the one component of the E2 will be also higher in energy, and but it will be in between 4A1 and 3A1, but in between. I am very qualitatively I am discussing. So, you probably have seen that I have used A and B here, okay. A and B, if you have taken group theory, or if you can recall the Millikan symbols you used to use, that A and B actually comes for that is for the smaller case A and B comes for the orbitals, and these are basically to identify whether upon rotating through a axis whether the phase is changing or not. So, here you will see that if we change through, if we rotate through a C2 axis, okay, you will see that your here plus, here plus. So, again here plus, if we consider this is plus and this is the plus. So, if I rotate, the phase will not change, but here you will see if I rotate here, okay, through C2. So, initially this the minus, that is the red. Now, if we rotate, the phase will of the lobes will change. So, in that case it is B. So, if it is symmetric with respect to a axis rotation, then it is A, and if it is not symmetric with respect to a axis rotation, then it is B. Okay. Similarly, for dz square, it is falls in the A symmetry. Okay. Okay. So, now what will happen, you see that A1 and E2, okay, A1 and E2 now splits into 3 orbitals, that is the A1, B1 and A1, and where you will see that dz square resembling orbitals is in the lowest in energy between these 3 d orbitals, and the A1 and 2B1, okay, are A1 is the highest in energy and the B1 is the in the middle. So, it will also gain in energy, but not as A1 4A1. Okay. So, 2B1 will be in between the 4A1 and 3A1. Okay. So, this is the most 3-1 is the most stable. Most stable means among these 3 orbitals, and this is the least stable. Okay. So, you see when I am changing the symmetry D5H to C2V. So, what I am doing? I am doing high symmetry to the low symmetry. Okay. So, then you will see that my 3 set of the 3 d orbitals further splitting, and one is going in high energy and one is going in low energy and one is in between. So, I am getting now 3 orbitals with different energy. Okay. Now, we will try to understand with some specific examples. Okay. So, here you will see I will just point out some of the important criteria what will be needed for my future discussion. So, you will see here 4A1, that is the 4A1 and 2B1. Okay. So, 4A1 and 2B1, that is what are the 4A1 and 2B1. So, this 4A1 2B1 basically the dxy and dx square minus y square is coming from the dxy and dx square minus y square orbitals. Okay. So, 2B1 is actually xy and 4A1 is actually the x square minus y dx square minus y square. So, this if you see the lobes and if you consider this coordinate, then the 4A1 and 2B1 orbitals are directed towards the open side of the Metallocene wedge. Okay. Open side means I am telling the this side, this is the open side. Fine. Now, you will see that say 3A1. So, 3A1 orbital resembles dz square orbitals, very obvious. Okay. So, the 3A1, 4A1 and 2B1 orbitals in Metallocene constitute three frontier orbitals, okay, which will be used for other ligands. Okay. So, which will be used for bonding to other ligands. Okay. I am writing L. So, what I am telling that Cp2Zr, okay, we know, but it is a +4 oxidation state. So, I will have other groups R2, that R may be X, may be halides, aryl, alkyl. Okay. So, these three set of orbitals, okay, that one is very important. This actually your, okay, will dictate the bonding and reactivities of the bent metallocene. Okay. So, let us try now, okay, by taking a particular system. Okay. So, this is a perfect example, okay, how this will vary. So, what we have done here, okay, very systematic way, okay, so that it is easy, it will be very clear to you. So, this one, you know that these are all the bent metallocene, no. So, all are bent metallocene, but L is different. Okay. If you consider like Cp2 M and L3 category. So, here L is equal to 1, 2, 3. Is it clear? Okay. Now, here let us say this is the rhenium. Okay. So, this is the D4 case, okay, and this one, okay, will okay. So, this is for molybdenum and tungsten, they are the same group, okay, and this here metal is the niobium and tantalum. Okay. So, metals are different, and here oxidation state is 3, here 4 and here 5. So, this is 3, this is 4 and this is 5, okay, and this is D0 case. Okay. So, there is no d electron, okay, and here, okay. So, we will see, okay, after understanding the molecular orbitals, that it has two lone pair. Do not worry, you will discuss how the two lone pairs are coming. Okay. I am just writing, okay, that how many lone pairs are there. Now, we will try to understand that how the two lone pairs exist in this kind of bent metallocene. Now, here you will see that one lone pair, very interesting, and it is very important to understand, and here you will see the no lone pairs, and what is the consequence for the no lone pair. Okay. Let us understand. Okay. Fine. Okay. So, now I am coming to the first case, where I told that there should be two lone pairs. Okay. Now, you see that this is the D4 cases, D4, and this is my +3 oxidation state, and the metal is rhenium. Okay. Now, I have a one bond. Okay. Let us covalent bond, that is with the hydride MH. So, one MH bond, okay, that means one S atom. Then again I am again doing the same approach as we constructed the molecular orbitals for the ferrocene. So, here you will see these are the resultant molecular orbitals for the bent metallocene. So, these are, okay. Now, I am now considering the one hydrogen bond, that one MH. So, this is my S orbital of the H. Okay. Now, what will happen? This A1, okay, and this A1, that is the 4A1, okay, you see that this s orbitals and this s orbitals and this d orbitals, the 4a1 orbitals, that is the dx square minus y square, can interact and form again one the bonding and one the anti-bonding like molecular orbitals, and this a1 and b1 will be non-bonding and here non-bonding. So, your this is 2b1 is the here HOMO, okay, highest occupied molecular orbitals. So, this is the 2b1 with highest energy which have the fully occupied electrons. So, here you will see that two non-bonding molecular orbitals. So, these basically are the lone pairs, okay, for this Cp2 MH, that is the one example like Cp2 ReH. Now, what will happen if I go to the next system, that is the this one, okay. Let us see. So, here I have now 2 MH. So, I have to consider the 2 H. So, now one is the bonding and one is the anti-bonding, okay, possible. Now, here you see that I have a A1 and I have a B1, okay. So, this A1 will interact with the this one, okay, because symmetry is matching, and this B1 again is interacting with the B1 symmetry of the d orbitals. So, because symmetry is matching, okay. So, this is, you will see that how the symmetry is allowing to understand the interaction between the LGOs of ligands and the molecular orbitals of the bent metallocene. So, as I told that this approach is called the SALC, that is the symmetry adapted linear combination approach. Now, here you will see, now this is my non bonding. So, this is the non bonding. So, that means this is my lone pair. So, you will see, okay, that this will have one lone pair. I wrote here, okay. So, one lone pair, and due to this scenario that this molybdenum Cp2 H2 have one lone pair, okay, and in which orbitals these lone pairs are? This is in the 3a1, okay, that 3a1, that is the this one dz square type of in orbital the lone pair is housed, okay. Now, it is clear, very easy, okay. Now, let us see what will happen in the next system, this one Cp2 tantalum 3 hydrides. Let us see what happens, okay. So, here 3 MH, okay. So, you know that this is very famous catalyst, we will discuss in the next class, okay. Very famous catalyst for to make the deuterated aryl compounds, okay. So, here you will see that I have now 3 hydrogen. So, we have to, this is the nodal plane, this is the nodal plane, okay. Now, I have A1, now I have B1 and I have another A1, okay. Now, if you match with the symmetry again through the SALC approach. So, what will happen? The B1 is matching with this one. Now, this A1 is matching with this one, okay, and this A1 is matching with this one, okay, this A1, okay. So, this one is matching with this one. So, what will happen? No non bonding okay, orbital, no lone pair. Okay. So, for tantalum this is the D0, okay, you will see there is no lone pair, okay, because all are in a bonding situation. So, this approach, okay, is very easy, very qualitatively I have discussed to understand the electronic nature of the bent metallocene, okay, because all are very important category of the bent metallocene which have lots of applications in synthesis, okay, in organic synthesis and also in polymer synthesis. Okay. We will understand now that we have a, what we have done so far, we have tried to understand with a series of bent metallocene where we saw that I have increased the metal ligand, that is the here in this case metal hydrogen, from 1 to 3 numbers, okay, with of course with different metal centers. Now, with this knowledge, okay, we will try to understand what will be the scenario for the ZrCp2, because this our main interest. Okay. So, students, here Cp means eta 5. Okay. When I not write anything, it is actually the eta 5. Okay. Now, here you will see that what scenario will fall here. Okay. So, here it is again D0 and this is 16 electron system. Okay. Sorry, D0 16 electron system. So, here it is zirconium, it is in +4 oxidation state and this X may be as Cl or R, okay, or H. Okay. So, both are hydride, both are Cl, both are R. So, in this case again you see that there is no. So, if we see, if we do the similar, so here also it will be like your Cp3, sorry, here Cp2 tantalum H3. Okay. So, in this case also you will see that your the dz square orbitals, that is which is actually the 3a1. Okay. So, this is the 3a1. The 3a1 is actually resembling to dz square orbitals. So, this dz square orbital is empty, has no electron pair. Okay. So, this is important to understand why it is like that. So, you have the empty dz square, has no electron pair. Okay. So, that is why this one can act as pi acceptor. Now, if it is a pi acceptor, because the dz square is now empty, so this can act as a acceptor, okay, for a ligands which have a pi orbitals. As example for, can you guess what may be the ligand? Yes, it is alkene. Okay. So, it can interact with alkene. Now, you now can you understand what we have, why we have discussed so much? Because yes, because this kind of compounds, the metallocene compounds, bent metallocenes are actually the catalysts for olefin polymerization, as example ethylene. Now, why it reacts with ethylene? This you have to understand, the fundamental question, how? Okay. Because for that you have to understand this molecular orbital theory. Okay. Fine. So, from here you saw that it has a empty dz square type of orbitals, that is the actually 3a1 orbitals, and these orbitals can act as a pi acceptor for the ligands like ethylene. Okay. So, that is very important, okay, to understand, and for to understand this we discussed in a systematic way using the molecular orbitals or SALC approach. Okay. Now, one very interesting another interesting aspect I will discuss very shortly with again some a series of compounds. So, here I am Zr Cp2 Cl2, okay, Nb, that is niobium Cp2 Cl2, and I am writing the MO Cp2 Cl, MO means molybdenum. Okay. Now, this is we know 16 electron, and this is the D0 system, this is the D1 system, and this is the D2 system. Okay. Now, if we see the angle, okay, because from the angle you can understand the electronic nature of the this kind of Metallocene complexes, that is why I am trying to understand. Okay. So, if I see the angle, okay, here, okay, you will see that this is 97.1 degree, this is at the experimental angle from the single crystal X-ray crystallography, this is 80.56 degree, and this is 82 degree. So, can you now correlate that what is the relation between this angle, that is the metal chloride angle, and the electronic nature of that dz square orbital? Okay. Can you correlate? Yes, you are right, that presence of electron in dz square like orbitals, that is the here 3a1 orbital, okay, causes smaller XMS angle. Okay. So, this is also important. Fine. So, if there is a electron, in the dz square orbital, it has a two impact. Okay. Why I am discuss? One is the electronic, and one is the openingness on Metallocene wedge. Okay. So, here you will see that in this case of zirconium analog, this angle is more 97.1 degree, okay, that is the CL/MCl. That means the openingness, that is the substrate can easily approach. Okay. But when we have electrons in this 3a1 orbital, as example for the niobium Cp2Cl2, the angle is reducing, like here 85 degree. If you have molybdenum where 2 electrons in this 3a1 orbital, it is further reducing. So, here you will see that in this case of zirconium analog, this is the perfect system, both in view of the electronic nature and also the view of the angle or openingness in the Metallocene wedge side. Okay. So, in conclusion, okay, we discussed in this class that bent Metallocene has unique features, okay, electronic, structural, and these unique features is actually dictates the reactivities. Okay. So, in the next class we will take some of the bent metallocene and we will highlight, okay, or we will discuss the key reactivities and the properties before going to the polymerization reaction. So, these are the reference books you can consult for the last two classes discussion, the Crabtree or Hartwig, or also you can also see the Hui book. So, thank you and see you in the next class.